the three basic trigonometric ratios: sine, cosine and tangent. These ratios can be defined by using a right-angled triangle. Let's consider the lengths of the three sides. The side opposite the right angle has length r, the side opposite angle theta has length y, and the third side, the side adjacent to angle theta, has length x. The sine of angle theta is defined by sin theta equals y over r. The cosine of angle theta is defined by cos theta equals x over r. And the tangent of angle theta is defined by tan theta equals y over x. These ratios could be defined in terms of the other angle, angle phi, in which case the sine of angle phi, sin phi, would equal x over r. The cosine of angle phi would be cos phi equals y over r. And the tangent of angle phi, tan phi, would be x over y. Defining the ratios from this right-angled triangle restricts theta to lie between 0 and 90 degrees, or 0 and pi over 2 radians. This is because the angles in a triangle must sum to 180 degrees, or pi radians. We want to be able to work with any angle: 0, 90 degrees, or pi over 2 radians. Angles more than 90 degrees, more than pi over 2 radians. In fact, any positive or negative angle. To evaluate the sine, cosine or tangent of any positive or negative angle, the right-angled triangle is going to be used again. But appropriate signs need to be given to the lengths x and y, according to the quadrant in which theta lies. Let's explain this using the Cartesian axes. The four quadrants are defined like this: first, second, third, fourth. For a point P that lies in the first quadrant, both the x and the y coordinates are positive. If P lies in the second quadrant, then the x-coordinate is negative and the y-coordinate is still positive. For a point in the third quadrant, then both the x and the y-coordinates are negative. And for a point in the fourth quadrant, then the x-coordinate is now positive, but the y-coordinate remains negative. We will rotate a line OP about the origin O. Theta is the angle of rotation measured in degrees or radians from the positive x-axis. Anti-clockwise rotations are measured as positive angles, and clockwise rotations are measured as negative angles. Evaluating sine theta for the general angle theta. Let's rotate the line OP, where OP has length 1 unit, anticlockwise about the origin, and investigate what happens to sine theta as theta increases from 0 to 90 degrees in the first quadrant, 90 to 180 degrees in the second quadrant, 180 to 270 in the third quadrant, and 270 to 360 in the fourth quadrant. Let's complete our triangles by dropping a perpendicular from P to the x-axis. labelling this point Q. Now, sine theta is going to be PQ divided by OP. But OP is of length 1. Therefore, sine theta is going to be given by PQ. In the first quadrant, theta increases from 0 to 90 degrees. When theta is 0, PQ is 0. When theta is 90, PQ is going to be equal to OP, 1. Therefore, as theta increases from 0 to 90, sine theta is going to increase from 0 to 1. In the second quadrant, theta increases from 90 to 180, but PQ decreases from 1 to 0. Therefore, sine theta decreases from 1 to 0. In the third quadrant, theta increases from 180 to 270. PQ changes from 0 to -1. Therefore, sine theta is decreasing from 0 to -1. In the fourth quadrant, theta increases from 270 to 360. And PQ changes from -1 to 0. Therefore, sine theta is increasing from -1 to 0. Now we know how to calculate the sine of any angle, we can draw a complete graph of sine theta, with theta plotted on the horizontal axis and sine theta on the vertical axis. Here is the graph of sine theta, where theta is measured in radians. It confirms our observations from the previous slide. As theta increases from 0 to pi over 2, sine theta increases from 0 to 1. As theta increases from pi over 2 to pi, sine theta decreases from 1 to 0. And this continues. As theta increases from pi to 3 pi over 2, sine theta continues to decrease from 0 to -1. And as theta increases from 3 pi over 2 to 2 pi, sine theta increases from -1 to 0. After 2 pi, the line OP from the previous slide begins its second rotation about the origin. This is shown in the diagram by the graph of sine theta repeating itself after 2 pi radians or repeating itself after 360 degrees. Thus, the sine function has period 2 pi or period 360 degrees. We can express this by writing sine theta equals sine theta plus or minus 2 pi k, where k is any positive or negative integer. Now let us compare the graph to the right of the y-axis with the graph to the left of the y-axis. Our observation is now that the sine of minus theta equals minus the sine of theta. A third very useful observation from this graph is that sine theta is equal to sine of pi minus theta. If I choose a value of theta, say between 0 and pi over 2, and then go vertically up to the curve, and then horizontally to the right until I meet the curve again, and then back down to the horizontal axis, we observe that the sine of theta, that angle between 0 and pi over 2, and the sine of theta and the sine of pi minus that angle are equal. This property can also be demonstrated from the Cartesian axes used on the previous slide. We should now be able to evaluate the sine of any angle, or at least express the sine of any angle in terms of the sine of an acute positive or negative angle. Let's try the sine of minus 500 degrees. This is going to be equal to the sine of minus 140 degrees simply by adding 360. Using that property sine minus theta equals minus sine theta, I can write this as minus sine 140 degrees, and of course that's going to be equal to minus the sine of 40 degrees. Let's now look at cosine theta. As with sine theta, we can use the Cartesian diagram with the right-angled triangle to evaluate the cosine of theta, where theta is any positive or negative angle measured in degrees or radians. Cosine theta is going to be OQ over OP. But remember, OP was of length 1, so cosine theta is going to be equal to OQ. In the first quadrant, that's going to be positive, in the second quadrant, negative, in the third quadrant, negative, and in the fourth quadrant, positive again. Let's now look at the graph of cosine theta and identify some useful properties. As with the sine function, the cosine function has period 2 pi, or in degrees, 360. This means that cosine theta is going to be equal to cosine theta plus 2 pi k, where k is any positive or negative integer. We also observe that the graph to the right of the y-axis and the graph to the left of the y-axis are mirror reflections. Therefore, cosine minus theta is going to be equal to the cosine of theta. If we want to express the cosine of minus 19 pi over 3 as a cosine of an acute angle, then we could simply add 6 pi to give us minus pi over 3. The cosine of minus 19 pi over 3 is equal to the cosine of minus pi over 3. And this equals cosine pi over 3. Now let's take a look at tangent theta. Starting with the Cartesian diagram as before, tan theta equals PQ over OQ. When theta equals pi over 2, OQ equals 0 and PQ equals 1. Therefore, tan theta is undefined because we are dividing by 0. A similar observation can be made when theta equals 3 pi over 2. OQ equals 0 and PQ equals minus 1. Therefore, the tangent of 3 pi over 2 is undefined. Now, looking at the graph of y equals tan theta shows that when theta equals pi over 2 plus or minus any integer multiple of pi, y equals tan theta is undefined. What else does this graph show? It shows that y equals tan theta is periodic. Unlike sine theta and cos theta, the period is not 2 pi, but pi. Therefore, tan theta equals tan of theta plus or minus k pi, where k is any integer value. Comparing the graph to the right and to the left of the y-axis, we observe that the tangent of minus theta is equal to minus tan theta. Let's express the tangent of minus 700 degrees as the tangent of an acute angle. We can simply add 4 times 180 to give tangent of positive 20 degrees.